Let's show one of the many applications of the derivative function by analyzing f of x using the first and second derivative rule. So let's show the many application of the derivative function by using the first and second derivative test in analyzing f of x. In this particular example, we have f of x is equal to x to the fifth minus 5x plus 2. And I am going to show you the graph of this function just to review on some of the terminologies that we needed to be able to describe the behavior of the function using the first derivative test and the second derivative test. And in this function, we are seeing two vertices of our graph, and it's right here at x is equal to -1 and at y equal to 6. So that is our first vertex, and this is our second vertex, which is pretty obvious in looking at the graph because that is basically the easiest point that we can observe when we are seeing the graph of f of x. Another thing that we can talk about this function is when the graph is increasing and when the graph is decreasing. And to be able to check when the graph is increasing and decreasing using the calculus language, if you assign any point in this interval, which is anything less than -1, let's say this point right here, if you draw a tangent line that will touch this point, you will notice that your line will have a positive slope or a line that is increasing. And if you pick a point or any point in this interval, all the slopes of your tangent line will be positive. And when that happens, we know that this function is increasing in this interval. However, if we pick a point, any point in this interval, which is any number in between -1 and +1, right here, +1, you will notice that our slope is going to be negative because if, let's say, we choose this point and draw a line or a tangent line that will touch this point right here, the slope of that tangent line is going to be negative, and it will be true to any point in this interval. And on this third set of interval, which is any number or any x value that is greater than +1, we know that this function or f of x is increasing because if we choose any point in that interval for that particular graph, all the slopes of our tangent line will be increasing or positive. So therefore, by just observing the graph that is given to us, we can visualize and see that the function is increasing at the interval x less than -1 and x greater than +1, and the function f of x is decreasing in the interval -1 and +1. Another thing that we can observe in this particular function is the presence of the relative extrema. We know that this is relative maximum, and this is our relative minimum based on the vertices that we're seeing in our graph. And also, we can see that the concavity of our function, we have two concavity. One is concave down, and the other one is concave up, with a point of inflection right here, which is basically the point when the concavity is changing from going up to going down. And this ugly little sketch that I'm showing you right now is just a review of what we're supposed to be looking at for our function using the first and the second derivative of our f of x. So in observation, it's easy to find the relative extrema, the point of inflection, its concavity, and the direction of the function because the graph is shown to us. But using calculus, we need to be able to learn how to write our analysis. And you can write it in two forms. You can write it in sentence form, or you can write it using math notation. So for the direction of our function using the three intervals that we have seen in our graph, we know that the function is increasing in this interval, and we can write it in sentence form similar to this one. f of x is increasing from the negative infinity to x is equal to 1, or we can write it in mathematical notation similar to this one, which is a little shorter. And our goal is to make things a little shorter when we are writing analysis in mathematics. So we can write it as f of x is increasing, open parenthesis and close parentheses, negative infinity, comma, negative 1. And another representation of this notation, you can also write it as, if you want, it can also be x greater than negative 1. So both notations, of course, are acceptable, whichever you prefer. So we know that the f of x is increasing not only in that interval, but also in this interval. And we can write it as f of x is increasing from 1 to the negative infinity, or x greater than 1. And f of x is decreasing at this interval, which is between negative 1 and 1. And you can write it as so, between negative 1 and 1. Or you can also write it in this form, which is x in between negative 1 and positive 1, again, whichever you prefer. So from the directions of our function, we also observe the relative extrema. This is our relative maximum, which is at x equal to negative 1. And if you want to find the actual point of that particular value at x is equal to negative 1, just plug it into the value of f of x, and you will find the vertex at negative 1 and 6, which is our relative maximum. And the relative minimum, which is located down here at the graph, is given by x is equal to 1. Or if you want to show the vertex, plug it into the value of f of x, and you will have 1 and negative 2. So we have the direction, we have the extremas or relative extrema. Now, for our point of inflection where the concavity or the change of concavity is happening, it's going to be at this point, which is at 0, 2, and we can write it as POI at this point, which is 0 and 2. And for its concavity, we know that we have a concavity going upwards, or going downwards in the interval, which is negative infinity to 0. So we can write it in sentence form. F of x is concave down from negative to infinity, or negative infinity to x is equal to 0, or with a notation similar to this one. And we also have a concavity that is going upward in the interval 0 and positive infinity, given by this notation, which of course you can rewrite as, for concave down, you can rewrite this at x less than 0 or x greater than 0 for its concavity going upwards. However, our goal is not to analyze f of x given its graph. Our goal is to analyze this function without seeing this graph. And that is the challenge of calculus that we're going to be working on in this next stage of our work. So here we have f of x, and we're going to be performing the first derivative test, which is going to tell us the direction of f of x and also where the relative extrema of our function. So given f of x at x to the fifth minus 5x plus 2, the first derivative using power rule is going to be 5x to the fourth minus 5. And now the next step is to find the solution of our derivative function, because the solutions of our derivative function will give us the critical points that will help us find the relative extrema and when the function is changing from positive to negative in terms of its slope. So here, f prime of x is equal to 0 is the command we use in calculus to tell us that we're going to find the solution of the first derivative, which is basically setting 5x to the fourth minus 5 into 0. And by using algebra, we'll be able to find those critical numbers. So adding 5 on both sides and dividing both sides by 5, we'll have x to the fourth equal to 1. And by taking the fourth root of both sides, x is equal to positive and negative 1, which is an important point or important value in our analysis, because this will be our critical points where we can see when the slope of the function is positive or negative. So we're going to be using our sign chart, and a sign chart is what we're going to be using to manually see the direction of our slope without seeing its graph. And in this case, all we need to do is to create our interval, and we have three intervals right here. We have an interval which is here, negative infinity and negative 1, interval between negative 1 and 1, and interval between 1 and positive infinity. And again, forgive my handwriting because I'm trying to be careful not to touch my screen so that it won't crash. But you can also rewrite this function like so, or interval like this: x less than negative 1, x in between negative 1 and positive 1, and x greater than 1. A little ugly, but you know what I mean. So in this particular interval, we are seeing that we're going to check for the value of our derivative for any values of x that is greater than less than negative 1, and it could be negative 1, negative no, it can't be negative 1, but it could be negative 2, negative 3, negative 4, and negative 5. Why can it not be negative 1? Because at negative 1, the slope is going to be 0, because that is why it's our critical point. So that means if we assign a value of x at negative 1, and draw a tangent line at x is equal to negative 1, it will give us a horizontal slope. That means that our slope is 0. And all we're looking for is a slope of either positive or negative. So let's check it by assigning values to our f prime of x. And in this case, I chose negative 2. So by plugging it in to our f prime of x, we know that f prime of negative 2 is going to give us a positive value because 5 times 16 is a big number, and subtract it with 5 and it will still be positive. You don't need the actual value of your f prime of negative 2. You're just really concerned about its sign. And the sign is going to be positive for anything less than negative 1. And for the second interval, in between negative 1 and positive 1, we will assign a value. And let's assign 0 because it's the easiest number to use for a number between negative 1 and 1. And by plugging in 0 to our derivative function, we are seeing that it's giving us a negative value. Therefore, the direction of the slope for any values in between negative 1 and positive 1 is going to be negative. And for the third interval, which is anything greater than positive 1, assigning a value that is greater than 1, I went with 10. And plugging it with 10, we'll have f prime of 10. That is a positive number. I don't even need to complete it because we're just concerned about the value of our derivative function. So now that we established the signs of our derivative function, we know that this is positive. Going to a negative value will help us identify if the relative extrema exists. And in this case, we have relative maximum because the slope of the function is changing from positive to negative. So keep that in mind, that the direction or the signs of your derivative function will tell you the specific extrema that you are working on. And in this case, relative maximum is at x is equal to negative 1. And if you want to find its actual value, plug in the value of your critical number to your derivative function, to your original function, so that you will find its vertex. And the vertex for this point is going to be negative 1 and 6, and that is our relative maximum. And for the second extrema, we have a behavior of our slope from negative going to positive. So if that happens, we have a relative minimum in our function. And our relative minimum happens at x is equal to 1. And to find its actual vertex, plug in the value of 1 to your original function f of x, and you'll find its vertex at 1 and negative 2. And now that we know our relative extrema, all we need to do is to articulate our direction by writing when the function has a positive slope in the interval that we have established using our sign chart. So our first interval, which is anything or x that is less than -1, we know that the value of the slope is positive. Also, at x equal to 1 and the positive infinity. So again, you can rewrite this set notation into x less than -1 or x greater than 1 for the interval for our increasing behavior. And for the decreasing behavior of our f of x, it's going to be in between -1 and 1. You can write it in this form, or you can also write it like so. X in between -1 and +1. So these are basically our analysis using our first derivative test, which gives us the direction of f of x and the relative extremas of our f of x. And by this, looking at the original graph that we have seen a while ago, this is our relative extrema, this is the direction that is positive, and this is the direction that is negative, which we verified using our first derivative test. And we're not finished yet because we're now going to move on to our second derivative test, which what the name implies, we're going to be using the second derivative test so we can find the concavity and the point of inflection of our function, which we know exists because we already saw the graph of the function from our first slide. All we need to do is to prove it using calculus by using our second derivative. So x to the fifth minus 5x plus 2 is our f of x. F prime of x is 5x to the fourth minus 5, and our second derivative, represented by f double prime of x, is equal to 20x cubed. And just like what we did on the first derivative test, we need to find the critical points and use the sign chart to verify when the concavity is going upward and when the concavity is going downwards using our second derivative test. So to find the critical number, set our f double prime of x to 0, which is 20x cubed is equal to 0. And this is basically the command, again, that we use in finding the solution or the x-intercept of our second derivative, which is 20x cubed. And by solving it, dividing both sides by 20, it will still be 0. So x cubed is equal to 0. Taking the cube root of both sides, we'll have x is equal to 0. And this is our critical point that will help us in our sign chart. And now that we're ready for our sign chart, we know that we have two intervals that we need to take note of. It could be an interval between -infinity and 0, or 0 and +infinity. So you can rewrite it in set notation, or you can rewrite it as so. X less than 0 or x greater than 0. So let's check the sign of our second derivative, which is basically the concavity of our f of x, by plugging in a value for x that is less than 0. And in this point, I use -5 as my value of x to verify or check whether it's going to be positive or negative. And we know that negative times negative and negative is going to be a negative number. And if you multiply it with positive 20, it will still be negative. So we have a negative value for the first interval and for our second interval, which will help us find the concavity of our function. We'll plug in a value for x that is greater than 0. So here we know that the direction of our second derivative is negative. So this means that the concavity of this function is concave downwards, sad face for a negative value. And for the positive value, by plugging in the value of, let's choose 10 this time. So here we know that 10 times 10 times 10 times 20 is a big number, but that big number is going to be positive, which what we are concerned about is going to be a positive value, which means positive, a smiley face. So now that we have this concavity checked using our second derivative test, we know that the point of inflection exists because from negative to positive, there is a change of signs in our concavity. That means our POI exists. Because if both of them are negative or both of the concavity will be positive, that means POI does not exist in that particular functions. Perhaps it's a piecewise defined function. So in this case, we know that it's concave down between negative infinity and 0. And we know that the f of x is concave upward between negative infinity, supposed to be 0 and positive infinity. So not negative infinity. Or we can rewrite this as x less than 0 or x greater than 0 for a function that is concave down. And for this interval with the concavity that is going upwards. So for the point of inflection, just plug in the value of x, which is 0, to the original function, x to the fifth minus 5x plus 2, and you will find that point when the concavity is changing from concave up to concave downwards. So again, ignore this second interval because we know that it's wrong. It's supposed to be 0 and positive infinity. For our POI, to complete our work, all we have to do is to plug in the value of our critical number from our second derivative, and it gives us 0, 2, so that is our POI. And again, going back to the graph that we have seen on the first slide, we know that this is our POI, and this is when the concavity is happening, going upward and going downward. And here, aside from finding the values or the analysis for our function, we'll also be able to graph or sketch the graph of our f of x without the aid of Desmos or a graphing calculator, because at x is equal to -1, that's our first critical number or our first interval, or when the interval is happening. So this is our first interval. This is our second interval at x equal to +1. Again, forgive my lines, they're not straight. And for the y value, which is 6 and -2, that will be the height of our relative extrema. So this one is at 6 and the other one is at 2. And this point right here is when the first vertex is happening, and this is when the second vertex is happening. And we know that our POI is at 0 and 2 from our previous slide, and that is also our point right here. And by doing so, we have the scaffolding that will help us sketch the graph of our function, and by just connecting the dot, we know that this direction is going upwards from the negative infinity all the way to here, and it will change to a downward direction, and from this vertex, it will go up again. And now we're seeing the little sketch of the graph that we've worked on a little while ago. So this is another way of using the first and second derivative test. It will help us sketch the graph of our function by using the critical number at x is equal to -1 and x is equal to +1, and by using its extrema, or the y value of your vertices at 6 and at -2, we'll be able to find or sketch the graph a little easier, similar to what I'm doing right now, which is basically the cleaner version of my graph a little while ago. And for the POI, which is at 0, 2, we can sketch the graph, and we are seeing that the graph that we're able to produce by hand is similar to the first graph that I showed you from our first slide. And these are the many useful applications of the derivatives of our functions. By using the first and the second derivative test, we're able to generate the graph of f of x without the aid of technology and by just using calculus. This is Dr. E, and see you again next time. Bye!